We will continue with discrete time Markov chain. In the last lecture, we talked about the evolution of the homogeneous Markov chain. Particularly, we discussed about the state transition matrix, state transition probability matrix. And I explained the Chapman Kolmogorov equation. Okay. Now we will discuss about the marginal distribution of states at instant n. So suppose initial probabilities are given, suppose V is the state space, and we assume it to be finite dimensional. Initial probabilities are given. These initial probabilities we can represent as a vector like this P0 vector, which is probabilities at instant 0. So P0, this is the probability that chain is at state 0, like it is state 1 this probability, and this is the initial probability vector. Now we have to find out the joint probability that x naught is equal to I and xn is equal to j. So that we can write as probability of x0 is equal to I into probability of xn equal to j, given that x0 equal to I. So this in terms of transition probability, we can write that this is Pi0 into Pijn. Since we know the joint probability, therefore we can find out the marginal. So this marginal PMF is given by probability of xn is equal to j. So that is equal to, now over this expression is for state I. So now if I consider all these states, that is summation over I, probability that x naught is equal to I and xn equal to j. This overall sum will give probability that xn equal to j. So that way probability that xn is equal to j is given by this relationship. So this is equal to summation over I Pi0 into Pijn. So this expression we can get from Chapman-Kolmogorov equation. In matrix notation, particularly we can write Pn, that is probability vector at instant n, is equal to P0 probability vector at instant 0 multiplied by Pn, that is the n step transition matrix. And this is, we can write that from Chapman-Kolmogorov equation, this Pn is equal to P to the power n. Therefore we have this relationship that P0 and Pn will determine the probability of the state at instant n. So we can now consider an example. Suppose given P is equal to this is the state transition probability matrix, and also initial probability vector is given 0.2, 0.6, 0.2, because we are considering 3 states 0, 1, 2. Therefore two-step probability after two step, that is P2 will be P0, that is the initial probability vector, multiplied by P square. So this, if I work out this multiplication, matrix multiplication, we will get this as 0.256, 0.384 and 0.36. So that way this is the probability that this after at n is equal to 2, probability of state 0 is 0.256, similarly probability of state 1 is 0.384 and probability of state 2 is 0.36. Now we can continue in the same manner. Then suppose we want the probability of the state at instant n. So this we can again carry out same type of multiplication. Here I can do p to the power 20. This ultimately we get like this 0.2105. This is the probability of state 0. Similarly, state 1 probability is 0.3158 and state 2 probability is 0.4737. And if I consider this probability that instant 21, then also we get the same quantity. That means this example suggests that this state probability sequence has converged. As n becomes larger and larger, this state probability vector will be stabilized. It will come close to some fixed quantity. So why this happen? Let us try to explain. So we will find out the steady state probability distribution. Suppose initial probability distribution is given by this p0 0, p1 0, like that pn minus 1 0. We are considering a n state Markov chain. So pn, that is the state probabilities at instant n, will be given by p0 into state transition probability matrix after n transition. So that way, now this quantity we can write in terms using the Chapman-Kolmogorov equation, that this is equal to p n minus 1 into p. So therefore, this now this quantity is equal to p n minus 1, that is the state probability at instant n minus 1. Now suppose these steady state probabilities exist. That means limit of pn as n tends to infinity exists. Then limit of pn as n tends to infinity will be same as limit of pn minus 1 as n tends to infinity. And suppose this quantity, this is a vector, row vector, we denote it by pi. That is, we are introducing a vector pi. This is equal to, this is the notation for vector. So we can write this as pi 0, pi 1, like that, pi n minus 1. So this is the steady state probability. Then from this equation and applying the limit, so pi is equal to, this quantity also will become pi is equal to pi into capital P, that is the state transition probability matrix. So what we will get if we write, if we take pi p left hand side, we can write this pi into I minus p is equal to 0. So this is a homogeneous equation. A non-trivial solution of the above homogeneous equation exists only if I minus p is singular. So that is the requirement. I minus p must be singular matrix. Now we can find out steady state solution, that is the steady state distribution of the probabilities through the eigen analysis. Notice that suppose P is a stochastic matrix, its property is that P is, suppose this is P11, P12, like that, P1 n minus 1, like that. Similarly, next row will be, but if I consider this row and then multiplied by 1 1 1, like that, n ones. So if I consider this multiplication, I will get 1 only, because this row sum of the stochastic matrix, if we consider any row, that sum is equal to 1. So therefore, if we multiply the transition matrix by this vector 1 1 1, that will be same as, we will get 1 1 1 only, and that we can write as 1 into this vector 1 1 1. So therefore we have seen that this 1 is a eigen value for the stochastic matrix P, because we have this relationship P into, suppose x is the vector, this is the matrix, P into x is equal to lambda times x. So this is the eigenvalue equation. Therefore we see that because row sum of the P matrix is equal to 1, so this 1 is always an eigenvalue, and corresponding eigenvector is the column vector consisting of all ones. So lambda is equal to 1 is an eigenvalue of P with an eigenvector, that is the all one column. So this is one important observation. Next observation is, let us consider Vmax. Suppose V is equal to V1, V2, etc. up to Vn minus 1. This we consider a vector like this, and Vmax is equal to this maximum of mod of Vi, I is equal to 1 to 1, 2, etc. up to n. Let us consider one eigenvector V is equal to that is given by components are V0, V1 up to Vn minus 1, and suppose Vmax that is equal to maximum over I of these components Vi. So this is the maximum value in maximum magnitudes of these components. So then we can write Vmax is equal to Vmax multiplied by probability Ij summation over j, because this sum is always equal to 1. So now Vmax instead of Vmax, because Vmax is the maximum of Vi, so we can write is Vj. Suppose if I include, then this will be greater than equal to, because instead of Vmax we are considering the smaller values. And now because this is a positive quantity, I can take this Pij inside, therefore I will get summation from j is equal to 0 to n minus 1 mod of Vj Pij. Okay. Now we know that this is the sum of the mod, so which is always greater than equal to mod of the sum or modulus of the sum. So that way this quantity, now this we can write in terms of the inequality greater than equal to modulus of summation Vj Pij, j going from 0 to n minus 1. Okay. So from this, now we are considering an eigenvector, therefore this quantity is the eigen related to the eigenvector by this relationship lambda Vi. So therefore what we will get, that Vmax is greater than equal to lambda Vi mod of lambda Vi for I is equal to 0, 1, etc. up to n minus 1. So from this what we will get, that Vmax is greater than, because it is for all I is equal to 0, 1 up to n minus 1. So if we consider the maximum modulus, then also this greater than equal to inequality will be satisfied. Therefore Vmax will be greater than equal to mod of lambda times Vmax. So this implies that this mod of lambda is less than equal to 1. So what are our observation? First of all, lambda is equal to 1 is an eigenvalue of P, that is number one observation. Number 2, for any other eigenvalue, its magnitude is less than 1, that means mod of lambda is less than equal to 1. So these two observations are important for analyzing the steady state behavior of a Markov chain. Now suppose these eigenvalues are distinct. Eigenvalues are distinct, and in that case the P matrix can be diagonalized in this way, that is M inverse P times M, that is the lambda matrix. Lambda is the diagonal matrix of the eigenvalues, and M is the model matrix, consists of eigenvectors as a column. So M is the model matrix. This model matrix means this is the matrix of eigenvectors as a column. So from this what we will get is that this P can be now written as M diagonal matrix lambda into M inverse. So therefore P can be written in terms of the diagonal matrix like this, and this M and M inverse, M is the matrix of the eigenvectors. Now suppose the limiting probability matrix, that is P to the power n as n tends to exist. So and let us denote it by this bold pi. So this pi is the probability matrix. So therefore we can write pi as limit n tends to infinity M lambda M inverse to the power n, and using the property of matrix we can write this as M lambda to the power n M inverse. Now lambda is a diagonal matrix. We are taking the nth power of the diagonal matrix, and then we will examine what happens as n tends to infinity. So now lambda to the power n we can write it as, because first eigenvalue is always 1, and then other eigenvalues we are considering lambda to etc. to the power n. Then because it is a diagonal matrix, all will be powered lambda to the power n, like that lambda n to the power n. Now what happens? Suppose we are assuming that it is distinct eigenvalue and mod of lambda I is less than 1. So we are considering only one eigenvalue is of value 1, and rest of the eigenvalues are with magnitude less than 1. Now if we consider this power, because its magnitude is less than 1 each of them, so to the power n, as n tends to infinity, they will become 0. So we will have a matrix only first component 1. Okay. So that is the behavior of lambda to the power n as n tends to infinity. It will be converging to a matrix whose first element is 1 and rest of the elements are 0. Therefore if we this M matrix then multiplied by all this matrix 1 0 0 0 etc., all 0 remaining, all are 0 like that, and then M inverse. If I do this multiplication, we will get this matrix will be, all row will be same. This is pi 0, pi 1 up to pi n minus 1, suppose. These are the probabilities, but what we observed that because of this M and M inverse and multiplying by this, we get a matrix whose all rows are same. All rows are same. So this is a particular observation. So that way this state transition probability matrix as n tends to infinity, it will converge to a matrix whose all rows are same. Okay. Now let us see what happened to state probabilities as n tends to infinity. So steady state probability, that means what happens to steady state probabilities. So this will be initial state probabilities multiplied by this matrix, because this steady state probability matrix will be converging to this. Therefore this initial state vector multiplied by this matrix. Now I know that this row sum is equal to 1. So therefore if I consider this multiplication, then because this sum will be also equal to 1, so all will be multiplied by pi 0 and then sum up. So that way this sum is equal to 1, therefore first element will be pi 0 itself. Similarly second element will be pi 1 itself, and then last element will be pi n minus 1. So what we observed that this state transition matrix, limiting state transition matrix as n tends to infinity, consists of rows like this, and each row representing the steady state probability. So steady state probability, that probability of the state as n tends to infinity, that will be equal to pi 0, pi 1 up to pi n minus 1, which is given by the limiting values of the state transition matrix. So this is an important result. So how we derive this? Using the property of the that eigenvalues, because eigenvalues of P matrix, one is, we are assuming that 1 is 1, and 1 is always 1, one eigenvalue will be always 1, but we are assuming that remaining eigenvalues are also distinct and they are all less than 1, because that is the property. So because of that we get this result. Therefore under steady state pi is independent of P0. What is the initial probability? It does not depend on that. So this pi is this vector, this is a row vector, we call it as pi. Okay, so this is a pi, this pi is independent of P0. So this is the way we can find out the steady state probabilities. So this analysis is quite complex, because we have to find out the eigenvalues and eigenvectors, then only we can work out like this. We can observe the limiting probability in another manner also. Suppose this is the limiting probability vector, then this will be same as this limiting probability into P. If the limit exists, then with the constraint that, so we will have a set of equation, but this set of equation will be homogeneous equation. Now in addition to this set of equation, we will get additional equation, that is the this probability sum must be equal to 1. So if we solve these two equation, this matrix equation and this equation, then we will be able to find out the steady state probabilities. Of course we are assuming that these limiting probabilities exist. We will consider one example. Suppose a two-state Markov chain has the transition probability matrix P given by this. P00 is 0.65, P01 is 0.35, like that. Now in this case, to find the steady state probabilities, we will have this equation, probability vector pi 0 pi 1 multiplied by P will be equal to pi 0 pi 1. So this gives us two homogeneous equation corresponding to this column and corresponding to this column. These are the equation. 0.65 pi 0 plus 0.4 pi 1 is equal to pi 0. 0.4 pi 0 plus 0.6 pi 1 is equal to pi 1. And we have the constraint that pi 0 plus pi 1 must be equal to 1. So with this constraint, we can now solve this set of homogeneous equations, and we get pi 0 is equal to 0.53 and pi 1 is equal to 0.47. So we will consider a special case of state transition matrix, that is doubly stochastic matrix. Now we know that in the case of a stochastic matrix P, row sum is always equal to 1. So row sum always equal to 1 for each row. Now if the sum of elements in each column of P is also 1, then P is a doubly stochastic matrix. So in the case of doubly stochastic matrix, the following theorem gives a very simple solution of the state probabilities, steady state probabilities. If Xn is a Markov chain with doubly stochastic transition matrix P, then the steady state probabilities are given by pi j is equal to 1 by n for all states, j is equal to 0, 1 up to n minus 1. So this is the statement. So if P is a doubly stochastic matrix, that means column sum is also equal to 1. That we will examine if row sum is always equal to 1, but if column sum is also equal to 1, then this is the steady state solution. So proof is also simple. From this equation, steady state equation, pi is equal to pi into P. We have this scalar form of equation, pi j is equal to summation from k is equal to 0 to n minus 1 pi k into p k k j. So this is the result we get from this equation. And now if suppose this p k j sum from k is equal to 0 to n minus 1, that is each column sum is also equal to 1, then pi j is equal to 1 by n solves the above equation, because if I put 1 by n, here also 1 by n, pi k is equal to 1 by n, then we will get this sum will be equal to, because this sum in that case we will get that sum is equal to 1 by n is equal to summation 1 by n, pi k is also 1 by n into summation p k j, k going from 0 to n minus 1. Now this sum is equal to 1. This because column sum of the stochastic matrix is equal to 1. This is for a particular j, therefore we are considering one column. This sum is equal to 1. Therefore because this sum is equal to 1, therefore left hand side is 1 by n, right hand side is also 1 by n, and this equation is satisfied. So solve the above equation. Conversely, suppose pi j is equal to 1 by n is a solution. These are the steady state solution. Then again we will get that this is 1 by n is equal to 1 by n, we can take out, and into summation p k j, k going from 0 to n minus 1. Therefore from this again we get that summation of p k j, k is equal to 0 to n minus 1, that is equal to 1. So that p is doubly stochastic. Therefore we have proved that in the case of doubly stochastic matrix, the steady state solution, steady state probabilities are simply, if there are n number of states, then pi j is equal to 1 by n. So this way computation is saved in many application of Markov chain. To summarize this class, we have established that this marginal PMF, the PMF at instant n is given by probability of xn is equal to j is equal to summation over I pi 0 into pi j n I going from 0 to n minus 1 if there are n states. In matrix notation, that is probability vector at instant n is given by initial probability vector multiplied by p to the power n. We also observe that lambda 1 is an eigenvalue of p, and for any other eigenvalue mod of lambda is less than equal to 1. Then the above eigenvalue properties, that is eigenvalue, one eigenvalue is 1, rest of the eigenvalue magnitude is less than equal to 1. These properties can be used to find the steady state probability for pi j for j is equal to 0, 1 up to n minus 1 for a n state Markov chain. That also we analyzed. We also observed that if the limiting probability exists, then we can write it in terms of that steady state probabilities is equal to steady state probabilities multiplied by p, with the constraint that summation pi I going from 0 to n minus 1, that must be equal to 1. That way also we can find out the steady state probabilities. Finally, we considered a doubly stochastic matrix. For an MC, that is for a Markov chain xn n greater than equal to 0 with the doubly stochastic transition matrix P, the steady state probabilities are given by pi j is equal to 1 by n for j is equal to 0, 1 up to n minus 1. So that is the final observation we made. But this eigenvalue analysis or matrix analysis as a whole is computationally very complex, and also in the steady state analysis we made several assumptions. So because of that we could find out the solution, but how we can find out the steady state behavior of a Markov chain generally, that we will consider in the next class. Thank you.